Okay, students, this is example 2.4 from PC Sense textbook. And again, he is referring to example 2.2, which we have solved in the first part. And now it is asking for the transformer to determine its efficiency when the at 75% of the rated output. So there is a transformer who is giving output at 75% of its total output capability, and it has a certain power factor, and they want to calculate the efficiency of the transformer. So and this was the transformer. Actually, this is the transformer that we want to know. We will be dealing with in this example. So first of all, let's look at the formula for our efficiency. We have P output over P output plus P losses. So what are the two losses? We know that they are the core losses. So we have P output plus P core plus P copper loss. Now the P output for the transformer, we can calculate V2 I2 cos theta. This will give us the total power of the transformer, output power of the transformer. And what is this is the maximum rated output, but in our case it is 75% of the rated output, so it will become P out will be into 75%. So let's see what is the V2. V2 for our transformer was 220 volts, and but before that we can see that what is this? This is actually S. So the rating of the transformer is also given to us. It is as equals to 10 kVA, 2200 volts to 220 volts transformer. So this is already given to us. Or we can calculate I2 also, but we can write here 10,000. What is cos theta? It is also given. 0.6 is the power factor. And this is 0.75. So the P output for our transformer in this case is real power that is being out because of a very poor power factor is 4500 watts. So this is the one thing we have calculated, P out. That is 75% of the rated output. Now let's look at the losses and the core losses. So do we know that there was an experiment that they performed which was able to calculate the core losses? That was the open circuit test, in which all the power being absorbed was being absorbed by the core. That was 100 watts. So we have the core losses also. PC equals to 100 watts. And the third part that we have to deal with is to calculate the copper losses. And copper losses for our system can be calculated. Now look at this. When we were performing short circuit test, so when we were performing this test, we had the value of this power that we utilized as the main copper losses. But we should know this thing, that the power is not directly related, and it is actually equals to I short circuit square into R equivalent. So we utilize this value. If you can remember here, we calculated the value of R equivalent by this equation. So what will happen now is we have to calculate this P short circuit that was given here is actually all of the power that is being consumed in the copper of the transformer winding. So what we can do, this I short circuit that we used before will now, this equation will be written it like this for the copper losses. And if you will imagine this, if you can concentrate this, IH square into R equivalent H. From that equation we actually did this, ISC square into R equivalent H, this. So the thing is that now the current 4.7 ampere, 5 ampere was the rated current, but now this load is 75% of the rated current, right? So here we will be have 0.75 into 4.75 55 square into R equivalent H that we had calculated previously, that's for 10.4 ohms. And this will actually turn out to be copper losses equals to 121 watts. Now if we look at our equation, we have P out, we have copper losses. So if we put all these values here, so the efficiency for the transformer will be P naught is 4500 watts here, P out, and then we have 4500 plus 100 watts plus 121 watt into 100 percent, and this will become the efficiency of transformer is 95.32%. This will be the efficiency of our transformer at 75% of the load. So the next part is want us to calculate the maximum efficiency. Max efficiency, this means that, for example, we have a transformer and there is an input power and there is an output power. What will be the load? What will be the load that will determine that our transformer is giving us maximum efficiency? So because you might imagine that transformer should give us maximum efficiency at 100% of the load. 100% of the load, they have designed it so it should give maximum efficiency, but that is not true, because there is a certain condition, and the condition in a transformer for achieving maximum efficiency is when the core losses of the transformer becomes equal to the copper losses inside the winding of the transformer. This is the condition for maximum efficiency in the transformer. And if the condition is same, then the transformer will be operating at its maximum efficiency. So what we are trying to find out here is, we know that the P out for the transformer is here, for example, this is the secondary, this is the low voltage side in our case, I2 cos of theta. And so the first condition will be, we have to determine how much current this will have that output which will give maximum efficiency. That was the condition number 1. And the second condition that is also very important is the power factor of the load should be unity power factor, that is, it should be equals to 1. These are the two conditions when our transformer will be operating at its maximum efficiency. So to how to determine the current? How can we determine the current for this scenario? This can be done is we have the equivalent model of our transformer, and we are dealing with the secondary side. This is the transformer, this is the current that is flowing through the transformer, and this is actually referred to the low voltage side. So when our impedances were referred, we are talking about, because here we have 220 volts, and this is the current we want to know, and here the impedances are 0.014, resistance is 0.104. So all the losses are occurring at this side. So what is happening here right now is, what we want is, we want that our losses, that are copper losses that are occurring here, P copper, that is equals to this current, secondary current, that is I2 I square into R equivalent of this value, should become equals to core losses. This is what we want. So core losses, we know it is 100 watts. So we can calculate I2 from this equation, PC over R equivalent C, and we will have an under root. Core losses we know are 100 watts. R equivalent is, we know, 0.10. So I2 becomes 31 amperes. So for this current, the output will be at the position of maximum efficiency. So V2 is 220 and I2 31, and power factor, the second condition was it should be unity. So this becomes 6820 watts. 6820 watt, and if you want to calculate the efficiency, 6820 watt. 6820 watt plus copper loss plus core loss is 100 watt, plus copper loss, it is also 100 watt. Why this is 100 watt? We have calculated the current when it will be 100 watt, and this becomes 97.15%. So 97.15% is our, so this is 97.15. And what percent of full load does this maximum efficiency occur? So the percentage at this current, that is 31 amperes at this current, and we know that S equals to V2 I2. So what will S become? It will become 220 into 31, that is, S is 6.82 kVA. So this power is being outed. And what was the rated power for this transformer? It was 10 kVA. So the maximum frequency, so the maximum efficiency occurs at 6.82 divided by 10, 68.2% of the rated power. So if the transformer, what they are trying to say is that the transformer is designed, the transformer has to run 24/7 every day, every night for the whole year. So if we adjust the load that it should be around 70%, 68%, then our transformer will be having minimum losses as compared to if the transformer is run at 100%. So this was the reason why they have made you solve this exercise. I hope it helps. Thank you. Assalamu alaikum.